Hello, my name is Matthew Godwin, and today I will be giving a walkthrough on how to solve question number 2 on page 111 from the Nelson Advanced Functioning textbook. The purpose of this video is to give the viewer a better understanding of a concept known as IROC. My question was, for a person at rest, the function pt equals negative 20 cos 300 degrees t plus 100 models blood pressure in millimeters of mercury at time t seconds. What is the rate of change in blood pressure at 3 seconds? Now the whole problem will be centered around this function. In this question, this function represents a person's blood pressure. Blood pressure is measured in millimeters of mercury. This is important as it gives us the unit of our y value or pt value. Time is measured in seconds. This is important as well as it gives us a unit for our x value. In this question, we are being asked to solve for the rate of change at 3 seconds. Now this wording is very important as it tells us what concept we are being asked to perform. Due to the question only giving us one specific time, we will need to use our instantaneous rate of change or IROC concept because we are trying to find the rate of change at that one instant. Before we talk about IROC, we must first understand what is the rate of change. Rate of change is defined as a rate that describes how one quantity changes in relation to another quantity. When the rate of change of a relationship is constant, any segment of its graph has the same steepness. The constant rate of change is called the slope of the line. In grade 10, the whole curriculum was centered around the equation y equals mx plus b, and m was calculated by the equation y2 minus y1 over x2 minus x1. This is the same equation used for calculating rate of change. In grade 11, we were introduced to average rate of change or AROC. Due to grade 11 focusing on curved lines, suddenly finding rate of change was more difficult. However, this problem was fixed when we found how to draw a secant line. A secant line is a linear line that connects the function in two distinct points. By drawing this line, we could find two coordinates on the line, and by using the same formula as in grade 10, we could find our average rate of change. In grade 12, we were introduced to instantaneous rate of change or IROC. We were required to find the rate of change not over a period of time, but at an exact time. This was achieved by drawing a tangent line on the function. A tangent line is a linear line that only intersects the function in one spot. You'd find 2 points on that line, and by using the same equation we did in grade 10, we can find rate of change at one instantaneous point. This concept is the one we will use today. Now for a basic overview to solve this problem, we will need to first obtain two time values because right now we only have one. We will then sub the values back into our function and solve for the blood pressure at that time. We will then solve for rate of change between our two blood pressures, which will end up giving us hopefully the right answer. Before we start, let's analyze our function on Desmos. On the x-axis we have the time in seconds. On the y-axis we have the blood pressure. This function relates to our problem because of how blood pressure and our heart works. As the heart contracts, the blood pressure increases, and as the heart relaxes again, the blood pressure decreases. This function resembles a normal person's resting heart rate. Now looking back at our function equation, we can see how it relates to the graph. The function tells us that this is a negative cos graph, meaning at 0 seconds the function should be at its lowest point. It also tells us that the function has been vertically shifted 100 units up. The amplitude of this function is 20, meaning the function ranges 20 units up or down. The last thing it tells us is that it has a period of 300 degrees, which means the graph should have a period of 1.2 seconds. From Desmos, it can show us that our equation and graph are related. The blood pressure fluctuates between a low of 80 millimeters of mercury and a high of 120 millimeters of mercury, meaning, as we said, this function was shifted 100 units up and fluctuates 20 up or down from that spot. We can also see it is a cos graph, as at 0 seconds the function is at its lowest and is about to go up. Lastly, we can see our period was correct since this graph has a period of 1.2 seconds. From our problem, we can see at 3 seconds the function appears to be at a high of 120 millimeters of mercury. When a function is exactly at a max or min point, it can be assumed that at the instantaneous moment the rate of change is 0. This can be seen when drawing a tangent line on this point, as the line appears to be straight, meaning the function is either increasing or decreasing. Therefore, my first assumption is that the IROC of 3 seconds should be 0 millimeters of mercury per second. Now it's time to actually solve the problem. First, we must acquire two time values. Because we are given only one time value and require at least two values to solve for rate of change, we need to use an IROC concept of getting as close to the 3 second time value as we can. This means we are required to take 1,000th of a second off 3 seconds and add 1,000th of a second to 3 seconds to obtain our two time values. We now have two time values of 2.999 seconds and 3.001 seconds. Now we can sub in the values back into our equation. We can first sub in our 2.999 second time value into the function equation in place for the t variable. Then perform the calculation in your calculator, being sure not to leave out any brackets. Once you get your answer, make sure to keep all digits, as these numbers will be very close together and any rounding will change the IROC value. Label this process 1. Then take your other time value of 3.001 seconds and insert it into another function equation in place for the t value. Once again, perform the calculation in your calculator, being sure not to leave out any brackets. Once you have your answer, make sure to keep all digits. Label this process 2. Next, we will solve for our IROC value. When solving for rate of change, we will use the equation y2 minus y1 over x2 minus x1. However, in our case, we will use milliliters of mercury 2 minus milliliters of 1 over T2 minus T1. Now be sure not to mix up your values. Because we labeled our solution and equation 1 and 2, it helps to clear up any confusion on this step. So sub in our millimeters of mercury value from our second equation and subtract the millimeters of mercury value from our first equation. Then take the time value from the second equation and subtract it from the time value from our first equation. When solving this, it can be seen that our answer is 0 over 0.002. This does not mean we have done anything wrong. This is in fact our answer. At 3 seconds, the rate of change of blood pressure is 0 millimeters of mercury per second. Now, although this seems odd, it is in fact makes sense if we go back to the Desmos graph. When I add the time into the equation, a straight line is created that runs through the point 2.999 seconds. However, when I add the equation with 3.001 seconds, it appears that the line runs perfectly on top of the 2.999 second line. This means that the lines are identical, proving how the rate of change at this time is in fact 0 millimeters of mercury per second. Now we are actually not done with this question because this is a word problem. It does require a therefore statement. A therefore statement is simply where you restate the question and then insert your answer using correct units. Therefore, at 3 seconds, the rate of change of blood pressure is 0 millimeters of mercury per second. The real-life application of this can be found in the medical field. Doctors will measure a person's millimeter of mercury levels to determine their blood pressure. A normal blood pressure can be defined as having 120 systolic and 80 diastolic blood pressure, as seen in the question. Doctors would want to calculate someone's instantaneous blood pressure to see if it is abnormal. If the instantaneous measurement was to be abnormal, it would indicate someone having either a high or low blood pressure, which could end up being deadly. It can also help athletes to know their blood pressure. Athletes, specifically endurance runners, tend to have a different blood pressure because of how they have trained. Athletes are able to pump more blood around their body in the same amount of time as a normal person compared to a normal person's heart, as this allows an athlete to optimize their muscular endurance. In conclusion, this question required us to analyze the question through the grade 12 advanced functions concept of instantaneous rate of change. We were able to calculate 2 time values from 1, solve for blood pressure, and then solve for rate of change. Thank you for listening, and I hope this helps you in your future adventures with instantaneous rate of change.